The next concept that we said we're going to talk about, and this will be probably the more simple of them, is concentration. And when we talk about concentration, we generally talk about molarity. And you've probably had this also in chemistry, and we'll kind of just cover it one more time. And let's see. Boom. Okay, we're back to our camera. So concentration. Okay, and so concentration, when we say we have a 1 molar solution of something, let's just say we have a 1 molar solution of salt water or something. Okay, so 1 molar solution, that means there are 1 mole of sodium, or sorry, salt, this is sodium chloride to be more specific, in 1 liter of solution. All right, so that's what molarity means. So 1 molar, if we have a 1 molar solution of sodium chloride, that means there's 1 mole of sodium chloride per 1 liter of solution. All right, so we'll do kind of a simple example of this. And let's say we have 10 liters of a 1 molar solution of NaCl. Okay, so we have 10 liters of a 1 molar solution of NaCl. So it's very simple. We want to know how many moles is there? Question mark. Okay, so we'd start off with 10 liters. And 1 molar means there are 1 moles per liter. So that just simply means there's 10 moles. And I probably should have put 1 mole of NaCl here for bookkeeping purposes. All right, sorry about that. Okay, so here we were just using molarity as kind of a conversion factor. So let's look at a slightly more complex type of problem. And we'll stick with sodium chloride, and we'll stick with a 1 molar solution of sodium chloride. So we have 1 molar sodium chloride. Let's say this sodium chloride has a density. Actually, let's put it in terms of specific gravity, and I'll show you why in a little bit. So it has a specific gravity of 1.06, okay? And the reason why I'm saying specific gravity instead of just density is we're going to be doing things in terms of kilograms and cubic meters instead of grams per centimeter cubed. And so using specific gravity is just slightly more easier. So let's say we have this 1 molar solution, and it's flowing with a volumetric flow rate. Okay, so it has a volumetric flow rate of, let's see, what's a good number? Let's do 1.25 meters cubed per minute. Okay, and we know the specific gravity is 1.06, correct? And we want to know what the mass concentration of this is. Okay, so what is the mass concentration? All right, so we want to know what the mass concentration of sodium chloride is. And so we probably want to start with figuring this out, I guess. So I'm kind of pausing too much, I think. So we want to know the concentration of sodium chloride. And so we want to know that in terms of kilograms in a cubic meter. Okay. And so we want to first take a basis. In this case, we're taking a time basis. And there will be other instances where we are forced to take bases, and I will probably cover that in class or another video. But here we're taking a time basis because we want to eliminate the unit of time from this. So we're just going to say a time basis of 1 minute. So then we can kind of do everything without time because we're knowing that this is just happening in a snapshot of 1 minute. Okay. And so we know our concentration of sodium chloride. So let's kind of use some notation to start our calculation here. And we want to start off with what we know. So we know we have 1 mole of sodium chloride in 1 liter of solution. All right, so we have 1 mole in 1 liter of solution. And the molecular weight of sodium chloride is, I'm going to go ahead and put it in terms of grams per mole so we can kind of do a conversion. Hold up. All right. So there's a trick that I need to kind of point out before we carry this calculation on a little bit further. So you know there's different types of moles. We talked about it. So there's gram moles, kilogram moles, and pound mass moles. When we're talking about molarity, okay, and we say there's 1 mole in 1 liter of solution, when we say we have a 1 molar solution, this is actually gram moles, okay? So we don't want to forget that because the next conversions we make basically are done because we have to take this in terms of gram moles. So there's 1 gram mole in 1 liter of solution. Okay, so the conversion factor here becomes really, really important. And so the molecular weight of sodium chloride is 58.44 grams of 1 gram mole. 1 gram mole of sodium chloride. And if you look here, our unit is meters cubed. And so out of convenience, we want to do everything in terms of meters cube and kilogram. And so we're going to go through and do that conversion. So 1 kilogram is 10 to the power of 3 grams, or 1,000 grams. I kind of put it in 10 to the power of 3 just because I'm kind of running out of room in my paper. And a liter to cubic meter is there's 10 to the 3 liters, or 1,000 liters in a cubic meter. All right, so I'm going to kind of plug and chug here. It shouldn't be too complex. And the thousands kind of cancel. So you have 58.44 in a cubic meter. So that's the mass concentration. There's probably a simpler way to do this. but kind of chose to do it this way. Let me see. The reason why I kind of chose to do this is because we're given a volume fraction that's in terms of cubic meters, okay? And so we want to have our answers in terms of cubic meters, because the next question, which would be an obvious question to ask, is what is the mass flow rate of this stuff, or what's the mass flow rate of sodium chloride in this solution if we have this 1 molar solution of sodium chloride going with a volumetric flow rate of 1.25 cubic meters per minute. So we want to know what the mass flow rate is. And so let's say we want to know the mass flow rate per second. Okay, just for funsies, okay? So we know our volumetric flow rate is 1.25 cubic meters per minute. And we know we have a mass concentration, which we calculated up here, of 58.44 kilograms per cubic meter. Okay, and just so it turns out, we want to be finding this in seconds. Okay, and we know we're going per minute, so we'll just do 1 minute over 60 seconds. Okay, and say, are we going to get our mass flow rate? Let's check. So meters cubed cancels. Minutes cancels because we want to know it in seconds. So we're going to end up with mass per second. So yes, we will get a mass flow rate if we plug in chug with our handy dandy calculator. So 1.25 times 58.44 and divided by 60. And so the mass flow rate of sodium chloride in seconds, is 1.2 kilograms per second. Okay. Now, to kind of tie everything together with other concepts we've talked about today, why don't we talk about the mass fraction of sodium chloride in our solution? Okay, so what's the mass fraction? Let me write. What is that? Man, I'm writing it horrible. In our solution. All right, so that's going to be the ratio. Okay, so the mass fraction now is going to be, we can do it in terms of mass flow rates. So it's going to be the mass fraction of sodium chloride. I'm sorry, the mass flow rate of sodium chloride times divided by the mass flow rate total of your solution. Okay, so we already calculated the mass flow rate of sodium chloride in seconds. So we already did that. And now, earlier we said it was a specific gravity of 1.06. And so if you remember from the activity we did in class, specific gravity is you get your density by multiplying your specific gravity times you get your density by multiplying the specific gravity times the density of a reference. And the reference is generally water. And in this case, water is 1,000 kilograms per meters cubed. So we want to get the density of our solution. And we want to have it in kilograms and in terms of kilograms and meters, because that's the units we're dealing with for this problem. If we're dealing in grams and centimeters cubed, we'd be multiplying it by another number, namely 1 grams per centimeters cubed. But in this case, we're going to do 1.06 times 1,000 per meters cubed. Okay, so 1.06 times 1,000. So we have 1060. All right, so that is our density. Okay, so why do we bother doing this? Why do we bother finding our density? Well, we learned very earlier in this video that density can be used as a conversion factor between mass flow rate and volumetric flow rate. And we want to know the mass fraction of sodium chloride in our solution. And to get that, we need to know the mass flow rate of sodium chloride, which we've already calculated, divided by the mass flow rate of our solution, or mass flow rate total. And we were given a volumetric flow rate of our solution, yes? So we have to convert that volumetric flow rate to a mass flow rate. And to do that, we use our old friend density, which we just calculated from specific gravity. We use specific gravity in lieu of just saying grams per centimeters cubed because we're dealing with cubic meters. Okay, so we used our reference density of 1,000 kilograms per meters cubed for water to get where we're trying to get to. So the mass flow rate of our solution, in this case, excuse me, camera, in this case, mass flow rate of solution, we want to have it in terms of kilograms per second. And because we wanted to keep our units consistent, because in this case, just for funsies, I said, hey, man, what's the mass flow rate of sodium chloride in seconds instead of minutes, just to make it that much harder. Hooray. Okay, so we have a mass flow rate of 1.25, sorry, volumetric flow rate up here, volumetric flow rate of 1.25 meters cubed per minute of solution. Okay, always good to have some sort of bookkeeping that can keep yourself straight. We know we have 1060. All right, so 1060 kilograms per cubic meter of solution. Okay, so, we also know that 1 minute is 60 seconds. So let's see. Are we going to get the mass flow rate of our solution in kilograms per second? Let's check it out, folks. So cubic meter cancels, minutes cancels, so we're going to end up with kilograms per second. Yes, we're safe to fire up the old TI calculator. I don't receive money from TI, but I have a TI, which is not working right now. Clear. Yes, here we go. So 1.25 times 1060. I didn't show this on some of these, but I've been kind of showing the intermediary steps. So I got 1325. You can see my beautiful reflection, I think. And divided by 60 seconds. And I got 22.1 if we round up kilograms per second. And I'll double check. Yes, I got 22.1 kilograms per second. So up here, we said the mass fraction of our solution would be the mass fraction, or the ratio. I'm sorry, what is the mass fraction of sodium chloride in our solution? Okay, and so it's going to be okay because seconds are going to cancel, so we're going to end up with all the units will cancel actually. And so we're going to end up with a nice ratio. So we said, and I should have done it this way, I apologize. So the mass fraction of sodium chloride, if you can read that chicken scratch, is the mass flow rate of sodium chloride divided by the mass flow rate total. So the mass fraction of NaCl, good old-fashioned table salt, is the ratio of 1.2 kilograms per second. I'm not really doing the railroad track method because you kind of know the units are going to cancel. Feel free to do the railroad track method if you see fit. 22.1 kilograms per second, and that equals 2. Come on, TI, bear with me. Divided by 22.1, 1.2 divided by 22.1 equals 0.05. or if we multiply that times 100, we'll just go ahead and put 5.4%. I had some extra digits on my calculator if you care to inspect. Anyway, that concludes the video. If you have any questions, feel free to ask me in class or send me a quick email. I do warn you, I get bombarded with emails. I do apologize for any goofiness in the editing. I am doing this on a shoestring budget, so hopefully it's beneficial to you. And thank you very much, and have a good time doing mass and energy balances.